Just wait a few minutes, I guess. Is this working? It is. Just wait a few minutes to see if anyone else rocks up. Is it? I thought the worst week would have been week 7. Every week is always. Ah, okay. So we're lucky you rocked up today, is that what you're saying? Yeah, okay. If we could just make it an easy one. Finish up early, go home. Yeah. It's luck. Nope. Huh? That is a shame. If we were in mobile robots in a lab, maybe, but we're 3. It's 1 on Monday, 1 on Tuesday, and 1 on Wednesday. But at 3, I think it's already finished 12 to 2. Oh, I think it's 11 till 2. Yeah. And then the one on Monday is 10 till 1. Yeah, yeah. Viz? Okay. Well, I mean, I've only said that a million times, but you can make your own user interface, but or you could just use RViz. Shows you the LiDARs, the camera. You can input waypoint. It shows you the path that it drives. Shows you the map. Have I just disappointed? Like you spent like hours on this?
I was like individually making subscribers, all the notes I wanted, adding labels, buttons.
Oh well. Do we think we're going to get any more people? Normally we have a decent sized class. I think I'll wait a few more minutes. We didn't have this last week because it was a public holiday. Me. There was on Wednesday. I covered for Preton last Wednesday. There was 3 people in the class. So 1 more person in here will have doubled that class. Yeah, I did all the classes last week.
How much we're expected to write for the project? He just says whatever you think is reasonable for research.
Which project? I haven't looked at it.
It's 30.
I don't remember it. I did the unit 10 years ago or so. Oh well, we'll just get started then. Alright, so today we're looking at electrostatic problems. So electrostatic, as the word sort of implies, is the types of problems where we have charges that aren't moving, i.e. there's no current or current densities, right? And so we use Maxwell's laws to solve these problems. So a few things before we get into it. So say we have a charge, right? Q1 in space. It's going to have some sort of field coming out of it. And if we have a second charge in that space, Q2, it's going to feel some sort of force, right, from that field effect from the first one, and the first one will also feel some field effect from that, right? And so we can say that the force is going to be related to the two charges, and it's going to be related to the material that are in, and the distance between those two charges, right? And because it's a force in a direction, it's going to have some sort of vector associated with it, right? And so that's going to be a vector. So we've got the charge, it's got a vector field around it, which is the field, and any other charges within that field are going to feel some sort of force. And we've got some sort of relation between the field, which is E, and the force that this charge is going to feel. And it's going to be related to the charge, right? So you got the force is equal to the field times the charge. And we can bring this down to here. And so the electric field is going to have a relation Q2 over the space times the distance between it. And that's going to be, that vector is going to be normal to the two forces, right? But what we're really interested in is the fields in a specific area around something, right? So just make some space. So we want to understand the fields in a specific area, and we have an equation for this, flux, right? It's going to be the field, which is this field here, right? With the dot product of the area that field is covering, right? So we've got some sort of plate, got some sort of field, and then in that field we'll have a plate, right? And there's going to be some resulting flux from that. And if the plate the area is going to be, the vector for that is normal to that surface, right? So if that, and since we're doing the dot product, if that plate is perpendicular to the field, i.e. the normal vector from that plate is in line with the field, then we're going to have maximum flux. Oops. Right? Because we've seen with the dot product, I think last week, that if two fields are aligned, then they're going to have the maximum. If they're completely out, then they'll have the minimum. So if we had a plate like this, got the normal vector that way, then the flux is going to be 0, right? Because now the two vectors are perpendicular to each other. So this is a nice simple example. We've got a uniform field and a surface that's flat, but typically what we'll find is that the fields that we're working with are not uniform, and the surfaces are not going to be flat the whole time. So then we're moving into differential space. So let's say we have a field coming in, and it's something like this, right? And then we have some sort of plate that's like a curved surface, like this. It's no longer flat. Then we can't do our dot product. We're going to have to move into integrals, and then we're looking at a flux with the integral over the surface, which is also a vector. And so we're taking small bits of the surface and looking at that because the field is not uniform everywhere and the surface isn't a flat surface. And so this becomes more difficult. And we want some way to simplify this if we can. So one way we can do that is by looking at the Gaussian. So if we've got some sort of charge, in the center here, Q1, we can look at some sort of sphere around that, right? And we can look at the field coming from that charge, right? So this is going back to point charges, right? And at every point where that field is coming through the surface of this sphere, it's going to be, again, normal to that surface. So now we've got our surface vector is now again parallel with our field vector, right? And so then we can go back to our flux density with just the dot product. We don't have to worry about integrals. So we're looking at creating a Gaussian surface around the charge or the field so that we can go back to simplifying this, right? And so the total flux in this case is around the charge is going to be the same irrespective of the radius, right? Because we've completely encapsulated that field inside the sphere. So no matter what radius we go to, it's going to capture the entire flux no matter what, right? So it's going to be irrespective of that radius, and we just end up with something that's going to be charge over the like material type that it's going to be in, right? So we have an important finding here. Just erase this. So from Gauss, we have an important distinction that the field has some sort of relation with the charge in that that's encapsulated by that sphere, right? So we consider the closed surface around a charge, and the field times the surface area is equal to the charge, right? So if we have that closed sphere that we had before, right, the field is encapsulated by that surface. The surface is represented by that small ds, and that's going to be related, have some sort of relation to Q, and it's going to be on the material, okay? But we're not always going to be looking at a single charge. We might be looking at a sphere, right? So if we had something like this, we've got charges spread out across it, we'll have some sort of charge density. If we then look at a sphere inside this sphere, so if we want to encapsulate the entire field. If we made a sphere smaller than the sphere that we have with all the charges on it, this red sphere is the one that's got all the charges uniformly distributed across it. Just draw that. And if we look at a sphere with inside that, we're going to have a field of 0, right? Because there's no charges. If we look at a field, if we look at a sphere bigger than the charge density sphere, right? So if we look at something like this, then we're going to encapsulate the entire, or all the charges on that sphere, and so we get back to this, where the Q here is just going to be some relation to the charge density, right? Which is Q is going to be the charge density times the area, right? So we need to find a Gaussian surface where the field is uniform to simplify down to multiplication. That's essentially what we're trying to do here. We've got some sort of charges or some sort of field, and we want to create a Gaussian shape around that to make it uniform in some way. So if we consider a dipole, we're sort of jumping a bit everywhere, but we'll get to the problems soon. Just change my ink there. So if we have a dipole, which is two charges oppositely charged, and we keep them separated at a uniform distance, we'll have something like this, where the field between them is going like that, right? And if we put some sort of dielectric material between them, right, the material inside will be slightly polarized. So we'll have positive charges moving here, we'll have negative charges moving here, right? And that'll be all the way up here. So positive, negative. And that's going to affect our field, right? So we now have two fields instead of one. So electrons bound in the field, they become polarized. Inside the material, we'll have two different fields. So the red field is going to be our E from before. So E from before. But now we have some polarized field, and that's going to be added to that. And so sorry, I forgot to add the coefficient there. So in the free space, so times by E naught, and then P is the polarized field from here, right? So inside the dielectric material, and we call that new vector, that new field, the displacement field, right? But what we can do further than that is in a uniform field, in a uniform material, the field is dependent on the polarized field, right? Is going to have some relation to E, right? And so we can rewrite the displacement field is E naught ER, and ER comes from the relative permittivity of the dielectric material times the field, right? So we just take out that polarized field and rewrite it. So if we've got some dielectric material in there, we're including the relative permittivity there. But if there is no, if there was no dielectric material in the middle and we just had this set up, then this just simplifies down to E naught in free space, right? Yep. So then we have a relationship as well with the displacement field over a closed surface is going to be equal to the charges, and then we also have, if there is a field present, this is going to be added back in, right? And so we use this equation here when we're talking about materials, and we also have our differential form of that, which is going to be related to the charge density on those plates or in that material in there, right? So one other thing we have to discuss before we get into it is potential difference. So I'll just clear this off. So for potential difference, if you've got a field in an area, there is a potential to have a force on a charge anywhere in that field. So we have Q here. If you're going to force. So anywhere around that charge, there will be a field, and that field is sort of related to gravity, where if we move it further away, so we move it off to here, the force due to that field, right? So we have some force pulling going this way. That force is going to change. It could either get stronger or weaker depending on how we move through the field. And it's similar to gravity. You know, the closer we are to Earth, the stronger the pull of gravity is. The further away, we have more potential for falling, right? So there's a potential difference there. And if I had A and B here, there'll be some sort of potential between those, and it'll be sort of related to the field and the movement. And of course they need to be aligned, so if we had a movement in this direction and we have a field coming this way, right? So if I'm moving perpendicular to it, there's going to be no change in that potential difference. But if I'm moving with or against the field, then I'm going to have a change in that potential difference. And we can look at the, if a field's not uniform, we then have to look at the integral form. So if we're looking at the integral and we're looking at it changing over, so between B and A, we're going to look at the integral between those, and then L becomes the small changes in a non-uniform field, right? And then again, we also have our differential form of this, right? So the field diverges if there's a potential difference, right? Which makes sense, right? We've got divergence happening. Divergence is either in or out, depending on if the field is converging or diverging. So if we've got a potential difference, we're going to have some sort of divergence away or into. So with this, we have, we're going to focus on Gauss's laws, and we have relationships for Q, which is the charges, D, which is that displacement field, phi, which is going to be the potential difference, and the field E, right? So now we can start looking at capacitors, or capacitance, I should say. Are we all right so far? Yeah. So capacitance of two conductors system, so the total charge is 0, is the ratio of the total charges on one of the conductors to the potential difference between that conductor and the other. So if we have a look at this, so we have two we have charges at 2 points, so we've got Q and we've got minus Q. The total charge is 0 between those two, right? We've got some sort of relationship that's going to be Q divided by the potential difference between that. And so Q is going to be just the charge at one plate, right? It's not the two plates because the sum's to 0. And it's dependent on the two parameters. These two parameters can change, right? Depending on where you are. As we looked at before, the potential difference changes if it's not uniform or something like that, and the charges change as well. So we want to get this relationship in terms of, in some terms that remain constant. So we want to find some relationship of C that is dependent just on the constants, and they are the physical values, right? So we have two plates, and we have some sort of relationship for capacitance already, right? So C is equal to E naught ER when there's a dielectric material added. I might just do that in a different color. A on D. So all these parameters here are physical constants, right? And the ER is for dielectric materials. So capacitance is a positive quantity measured in units of farads. So we have some relationship of C. Now we're going to have a look at two parallel plates, right? So to understand how everything's working here, we want to hypothesize where the charges are and what type they are, if they're positive or negative charges. And we're going to determine the electric field given the charges which are the source of the field, make appropriate assumptions. So no fringe. So by no fringe, we essentially mean at the edge of these plates, we're going to have some curvature, right? We're just going to ignore that. Equidistant planes, assume that the field is uniform and independent of Y and Z. And then use boundary conditions, that's a potential difference between upper and lower. So we know that on a plate like this, we have some sort of battery V0. The top plate is going to be V0 and the bottom plate is going to be 0, right? And it's the simplest shape we can make. We've got two plates at a distance connected to a battery. Where are the charges, and can we determine the field between them, right? So if we have a conductor, right? So this is different to, this would be different to your dielectric material. And we have some field coming in this way, E. We're going to push all the positive charges to the edge of the plate here, right? And in a conductor, that leaves us with no free charges in this space here, right? So inside the conductor, we're going to assume that the charge density in that free space, oh sorry, not charge density, we're going to assume that the field at this point is 0 because the field's related to charge and there are no charges there now because we've introduced a field that's pushed everything down. So the charges will move to the edge of the plate as far as they can until they can't move any further. No charges inside the conductor, therefore the field inside the material is going to be 0. And then we have this equation over the surface is equal to 0, all right? Since the charge is at the edge. So where and what are the charges? Region of higher potential, net positive charge on upper plate, negative charge on lower plate. For the conductor, charge on surface, positive and negative attract. Positive on bottom surface of upper plate and top surface of bottom plate. So we end up with something like this, right? So you've got negative charges here, positive charges here, and we'll have some sort of field going like this. Now we do have, as I said before, we got those fringe values, right? If it doesn't tend to infinity, i.e. if the plates don't expand out to infinity, we're going to have some sort of fringe, and it's going to be a non-uniform field, but we're going to just ignore that so we can keep it as a uniform field, sort of staying away from the edges, right? So determine the electric field given the charges. So no free charges in the space between the plates, so the charge density is 0. We'll have, if we go back to our equations from before, let's keep this color. So we had before, C is the charges over the flux between, the potential difference between the two. We know that the potential difference is going to be V0 because it's connected to the battery, right? So V0 difference there. That's the potential difference. So what we want to do is we want to remove this V0 from this equation here. Okay, so we want to find some relation of the charges. It's going to be related to V0. So these two cancel out with each other to make things a bit simpler. Okay. We essentially have the charges, field, and the potential difference, and we're going to find some equations for the potential difference that apply using circuit theory to find, and we've done this before, in circuit theory to find the relationship in a transmission line, right? Where we had like the, what was it? The capacitor across there, and then your inductor there, and capacitance, and so on and so forth, right? So you had something like that. And we took, if you remember when we did that, something like that, remember? And we had V0 here, and then V0 at time plus delta, X plus delta X. That was X and T or something like that. And what we did was we found some differential equations that gave us our relationship. So we're going to do something similar for the potential difference, and then we're going to work our way backwards to get the field, and then from our boundary conditions we can get what the charges are. All right. Cool. So from Poisson's law, which Gauss has applied to a field between plates, we'll have E. This is related to that. So we have the displacement field is equal to the charge density. We also have this equation here. If we take the Laplacian, so we take the dot product E is then going to be related to the dot product of that, and remember that's our Laplacian term, right? So we'll have that is equal to this, and that's negative, remember, so we've got negative on both sides. So that cancels out, which gives us this here, right? And then we take the differential of those, it's got to be equal to 0. Oh, we're saying it's equal to 0, right? Because the charge density is 0, right? So this term ends up being 0. Previously, we also said that we're ignoring the x and y terms on that previous page, right? So based on our experimental setup. So there's no free charges. Now we know that if we've got a second order differential that's equal to 0, it means that the potential then is going to be some constant like that, right? Because when you differentiate that twice, if you differentiate it once, d phi dx is going to be c1, and if we differentiate it a second time, it's going to be equal to 0, right? So the solution to this equation here means that the potential difference has got to be of that form, right? So assumptions that the potential difference is independent of y and z. The Laplacian of the potential difference is equal to 0, so therefore the solution to that is going to end up with that. We then look at the boundary conditions. So we know at 0 distance here, the potential is going to be 0. And at A, it's going to be V0, right? So we can then find our values for C2 and C1 if we just put it into this equation here, right? So if we're at x equal to 0, that gets rid of this term. This is going to be 0 here, and that means we know that C2 is going to be equal to 0. And then for the second term, so now we don't have this, we're at an A distance from here. It's going to be equal to V0, and so C1 is just going to be equal to V0 on A, and therefore our potential difference is going to be V0 on A times X. Right, and so now we've got some sort of relationship, and we can plot that if we wanted to. X, it's just going to be some relationship like that, where this is going to be V0 at A, right? So now we've got some sort of relation, that's good. Now if we want the E, so remember we were going from potential to the field, and then we wanted to know what the charges was at the end, right? So the electric field is back from up here. It's going to be the negative del of the potential difference. So the absolute value of this is going to be V0A, and it's going to be in the direction of x, right? Because the field is this. If this is the x-axis, the field is this way, and we know it's negative, right? So if we look at this from just a logical point of view, the field E is coming down, and the amplitude of that is going to be V0 on A. All good? All right, so from there we want to work out what the charges will be, and then from that charges we can work out what C is, right? So Q, we're still working out an equation for C that's in constants, and we need to work out what Q is, right? So we've now got E, the charge density at just below A, so that's what this means here, just below it, is going to be the permittivity times the negative A, which is just, remember, AX is just the unit vector in the direction of X, and that's going to be dot product, come on, draw, dot product with the field just below A. If we take that, we're just going to get the permittivity and the amplitude, right? Because they're in the same direction but negative, and that's a normal component. So boundary between the conductor and free space, what conditions do normal and tangent components have to satisfy? So we can then work out what our charges are. The charge on a plate, right? So if we have the charge density, got some plate here, the total charge of this plate is just going to be the charge density times the area of that plate. So we got charge density times B times D, which gives us our Q relation. We can then substitute this back into here, and we'll get out that now our capacitance is just related to that permittivity times the plate size divided by the distance between the two plates. And if we had some dielectric material sitting in here, we would have to add in the, yes, we add in the ER term there as well. And so you could end up with a question like this of how to derive this if you had two different dielectrics or something like that, how that derivation would come about, or you could have two dielectrics like this, and so you'd be expected to work out how to do something like that as a question.
Would your A still be the same in that case?
Yes, because we had the uniform distance between the two.
So it still goes through the whole way? Like,
yeah.
Okay.
Yeah. If I understand you correctly, then yes. Yeah. And so you could also have more complex examples like, so we've just had like just a plate, but we could also have a cylinder where we have one side attached to a battery and the other attached to the negative. And so we'll have a look now at a coaxial cylinder. So you should be given the equation for this, the gradient of the potential difference for a cylindrical coordinate system. You just have the one on row. Really, that's the big difference. So with this, say we've got positive charges on the outer surface of the shell, of the inner shell, and we have negative charges on the inner surface of the outer shell, just to make it confusing. Assume for symmetry that the potential field is equal to, is a function of rho, so the field is only dependent on how far out along this row, right? And rho is equal to B is equal to 0, right? So at this distance here on this plate, our potential difference is going to be 0, and at this one here it's going to be V0, right? And again, we want to work out what the capacitance is, so we start with some potential difference, we work out what the field is, we work out the charge density, work out what the charge is, and then we can get a relationship for the capacitance. So if we have a symmetry, we take the derivative. It's only a function of rho, so we can ignore the other two terms back here. I will just ignore that one term, I guess. So we'll have that. And between the two cylinders, we've got charge density 0, so there's like nothing in here, right? So there's no charge density, therefore, for this one here, that's got to be equal to 0. And again, we end up with this term in here needing to be a constant. So we have this here, this has to be a constant term c, and if we have a derivative that's like this from earlier math, you would have df dx is equal to 1 on x, because c is just a constant in this case, we'll just make it 1. That then means that it's a function of ln of x, right? So the potential difference at rho is going to be a function of two constants with ln at rho. And again, we can solve this equation using our boundary conditions. So we've got at A, which is this inner plate, is going to be equal to V0, and at the outer plate it's going to be equal to 0. And we can solve that for C, and we'll get our potential difference out. The electric field between the cylinders is given by this. So again, we've just got more math. Surface charge density on the outer conductor and the boundary conditions gives us this, and that's the dot product. Boundary conditions, where the normal component of the field. What does the tangential component tell us? Essentially then we have cylinder, length, out to B. Our charge is going to be the charge density, which we have here, right? Just outside the B. And it's going to be times the area. The area for a cylinder is 2 pi B times L, where B is the radius and L is the length. And we should... So if we go to a closed surface, so we can also look at it as a closed surface. Actually, did I skip something? No. So we've got over a closed surface, the field is also equal to over the closed volume of that, which is equal to the closed surface of that. So ds is going to be 2 pi a dl, and again, this is just more math you can follow through. So for any length L along the inner conductor, the electric field just above A is going to be this here. And so we have our neutral conductor, we put it inside the field. There's a net zero charge, we put it in there. There's a transient period where the charges move back and forth. And then we'll have inside this material here in the middle, the field is going to be equal to 0. Similarly, if we have some sort of sphere, we put it inside, the internal field is going to be 0. Isolated neutral solid conducting sphere. So we put that in the middle. The core becomes irrelevant, right? So in here, doesn't matter what's in the middle. It's going to be the field effect from the outside. This field here is going to be 0. So essentially what that means is that the shield, there's a shield inside, right? Which is sort of like your coaxial cable or something like that. So same thing with, like, if you have a lift, right? A metal lift, the charges move to the outside of that, and the inside of that is shielded, so that's why you have no phone signal inside, right? So inside is shielded from external fields. So we consider a point charge Q at the center of an initially neutral spherical metal shell with a center at the origin of a sphere coordinate system. The shell has an inner radius of A and an outer radius of B and contains no material. So we've got no material sitting between this. We've got a charge sitting in the middle, right? And we've got our two plates set up again, right? So one's going to be positive, one's going to be negative. We'll determine the electric field for R greater than 0 and determine the electrostatic potential for R greater than 0. We remember E is equal to Q on epsilon naught 2 pi R squared. So start with this, the field for R greater than B for Gauss's law, closed surface, is going to be equal to 1 on epsilon closed volume, right? So that's just Gauss's law. We create some sort of surface around this, right? And we know that then that just is the dot product between those two, and it's going to be charged on epsilon naught. Shell has a net 0, no charge, right? So assume the field has symmetric symmetry. For the surface on a sphere, radius R greater than B, ds is going to be the normal in the radial direction. And again, just got the math coming out. So consider three families of Gaussian surface corresponding to the following region, or three regions. So between here and to the shell, from the shell to the outer shell, and then from the outer shell out to infinity. So we've got three regions there, right? And we know, so this is a point charge in the middle. This shell will have the negative charges, and this shell will have positive charges at its surface. And then we know the total charge on the plates is going to be equal to either negative or it's going to be equal to the positive, right? If we took a Gaussian surface at the center between R0 and, between 0 and A, we're going to encapsulate the entire point charge, which we're calling Q, right? So we would encapsulate that Q. If we took it between A and B, we're now encapsulating both the point charge and this outer shell, so it's going to be 0, right? Because the sum of the two is 0. And then if we take it for any surface outside of that, we're going to have the positive, negative, and then Q again. So it's going to again sum to Q at that point. So evaluate the total charge within the volume enclosed by each Gaussian surface. So that's the total charge over enclosed volume, charge density times the volume. So for the enclosed area between 0 and A, as I said, it's just going to be equal to Q, which is the point charge. When we look at the next area, we've got the point charge plus the negative, which is going to just sum to 0. Electric field is 0 in the conductor. If there is a charge, it resides on the surface. Mobile charges within a conductor would repel until they lie on the surface. Surface charge, blah, blah, blah. And again, if we move out past that, we have our Gaussian surface outside of there. We're now encapsulating positive, negative, and then the Q, so it's going to equal to Q again. And so the surface charge of same sign Q exists on the outer shell. So what this is telling us essentially is that outside, if we had a point charge in here, right, it's not going to feel any field effects from the outside, but anything on the outside is going to feel effects from the inside. Again, just math. Conductor is equipotential body. Potential is constant in the conductor. So if we plotted that out, so on the inside, right, this is what we would have some field coming in. Oh, sorry. This is, if we had something sitting in the middle between A and B, there would be no electric potential, right? Which means the potential difference doesn't change at all between those two plates. And then outside it would drop off again, and it would drop off moving out, right? Because as we move away, it's going to drop off on R cubed, right? So for no metallic shell. All right, so if we had charges sitting around, so if interior is neutral, then the shell shields the exterior from the interior, maintains balance in the interior. But if we have a charge here, if we had a charge here in the middle, then obviously the field outside is going to be non-zero, right? Between here, it'll be 0, and there'll be a field felt here, but on the outside it's going to be non-zero, but any field from the inside going, or from the outside going in is going to be 0, right? So the charge isn't going to feel anything from the outside. But if we had two charges in there, equal and opposite signs, then again we would end up with no influence on the outside. Okay?
And at like point, take the green circle in the middle, and that point outwards.
Which green circle, sorry?
So in the case where there's a positive and a negative point charge.
Yep.
Green,
yep.
Interior, you would make R bigger than that, still 0, right? Is it positive negative? That's well inside the...
Between these two plates?
Yeah.
No.
Oh, they don't. There's both positive and negative charge in there this time, right? Around the plate.
Oh, yeah, you're right. Sorry, yeah.
So you assume, I guess,
Yeah.
It doesn't matter the distance they are.
Yeah, the distance from the shell, I think it doesn't matter. Yeah. All right. That's pretty much it. That's all I really have on here. Actually, one last thing. Where am I? No, I want to go back. Where's my graphs? It's just a lot of math. So yeah, as I was saying before, we have the two like that. We'll have a potential fault on the outside, but if we were to, if we had a coaxial cable like this, Q in the middle, if we grounded the shield, right, then that's not going to have a negative charge. It's now just going to be, it's not going to have the positive charge. It's going to be grounded. So now you end up with a negative charge countering out the other one. So then on the outside, you'd have no, you wouldn't feel the field anymore from the inside, right? Windshield external area from internal. If you connect the outer shield to ground to remove positive charges, results in a 0 outside the shield. Does that make sense?
That means you could effectively not have shielding, right?
If you don't care about what's happening around the cable, then you could not have
An insulator around it.
well, you could just not use a ground.
Yeah.
But if you don't want to influence anything around it, then you could ground that shielding, which I think is quite common. But the only other thing, so like in like comms and stuff, you really don't want to have any sort of external noise. So you might ground the shield, but you would only ground it on one side, because if you ground it on both sides, you end up with ground loops as well, which creates more noise. So yeah, you might ground the shield to make sure there's no influence outside of that, because typically when you have those sort of applications, you probably have several coaxial cables running, and they'll shield each other, but it's never perfect, right? So whatever you can do to reduce it is probably good. Yeah, that's all I have in my notes. Is that all right? It's just a lot of math, which I don't want to talk about, so.
You got the quiz for this, I think, next week.
Is it?
Yeah. Just after this. Right. 1 second.
After this one? No, it can't be.
Up to this.
Huh? Oh, up to this. Okay, yeah, okay. How many quizzes do you have for this? 4?
Yeah, 4, so 2.
Yeah. Sort of hard to have much on this half so far, right?
He's probably going to ask like on vector stuff. That's all it is.
Yeah. Surely not. Just have Mathematica open. Yeah? Yeah. You still have to set it up a bit, but again, this project doesn't integrate. Just for anybody who's watching, we've finished. Someone's asking me about a different unit. So for mobile robots, yes, if you use others, that's fine, because the project is an integration project. It's not a. It's not like a build everything yourself, which is typically a normal robotics, like a roboticist would not build everything themselves. You would just use existing stuff. Yeah, I've said that a few times. So if there's no questions, you just can head off. You don't have to hang around.